Harmonic Oscillator. Based on Chan's chapter 2, we review energy levels and eigenfunctions of a harmonic oscillator. A particle of mass m subject to a linear restoring force Fx equal to minus kx, where k is the spring constant, results in one-dimensional simple harmonic oscillator with an oscillator frequency omega equal to square root k over m. So as shown here, yellow block, which is a particle with a mass m, is attached to a fixed wall with a spring, by a spring with a spring constant k. And here k is the spring constant, often renamed as elastic constant. Sometimes stiffness constant. So mass m is attached here by a spring with spring constant k, and corresponding potential is u, is quadratic as a function of x, equal to kx squared over 2. So du dx is equal to minus f. Okay. So this potential shape will be added into Schrödinger equation. Also, around the local minimum, any potential, here any potential means any arbitrary potential, can be described approximately based on quadratic potential. We will discuss more in later slides. And this is very useful in quantum mechanics because there exist analytic solutions for the quadratic potential. Quadratic potential is rather simple compared to some other potential shapes. Also, this is very important problem because, for example, the positions of atoms that form a crystal are stabilized by the presence of a potential that has a local minimum at the location of each atom, thus defining the lattice constant. You will see later on, if we wish to understand how the vibration motion of atoms in a crystal determines properties such as the speed of sound, heat transfer, then we need to develop a model that describes the oscillatory motion of an atom or about a local potential minimum. So this is actually simplified picture of general atomic structure in the case of atoms, not just one point mass. There are extremely many atoms connected with some elasticity between atoms. Okay, so we will describe things like mass m, connected by spring constant. Here k is the spring constant, not the wave number. They are different. But when you consider speed of sound, heat transfer based on phonons, actually you will actually consider dispersion between energy and wave number of phonons. So for the sound, you can draw this dispersion between energy and K. Then it is linear. This energy is proportional to h bar, and then speed of sound, then K. So this slope is related with the velocity. So larger the slope, larger the velocity. For the air, depending on dispersion relation, we check out the slope, then we can obtain the velocity in air. In crystal, we can also calculate energy and wave number of phonon relations. And for example, in silicon, the slope is much larger, and the velocity v will be quite large, like 8 km per sec. That is called as acoustic phonon velocity. Surely we cannot calculate the dispersion ourselves, but at least we'll try to understand the simple harmonic oscillator based on Schrödinger equation. So classically, the harmonic oscillator is described based on this Hooke's law, F equal to minus kx. Then using Newton's second law, F equal to ma, and this is same with the Hooke's law. So the acceleration is replaced by d square x dt square. This equation is very simple second order differential equation. So we divide both sides by m, and then k over m is replaced by omega 0 square. We have this equation. The solution is actually either sine or cosine, right? And then if we add them up, sine and cosine functions, then we can also further simplify, like a sine omega 0 t plus pi. So there comes phase information here. This phase actually determined by the initial condition, and kinetic energy T is equal to 1/2 mass m, then v square, velocity v. So velocity v is shown here, dx dt. So we take the time derivative, then as you can see, omega a, the sine becomes cosine, right? Cosine omega 0 t plus pi. So we take the square, and we have this one. Yeah, so 1/2 m omega 0 square, this is k. So k a square cosine square omega 0 plus pi. In the case of potential energy U, which is equal to 1/2 kx square. So we take the square here. So a square sine square omega 0 t plus pi. If we add them up, then we have total energy. Then surely sine square and cosine square, they add it together to be 1. So this is what we learned sometimes high school class, sometimes the freshman physics course. The importance of harmonic oscillator. We can appreciate the importance of harmonic oscillator by considering the general shape of the interatomic potential shown in figure 2.7a. So there is certain potential shape, so interatomic distance, atom and atom and their distance, it's like x prime. Okay. Depending on that x prime, the interatomic potential shape is changing. So depending on the atomic shapes, and also depending on types of bondings, there are different types of bondings. For example, you might have heard of covalent bonding. In each case, electron cloud for atom 1 and electron cloud in atom 2, they share with each other. Okay, so that eventually the octet rule is satisfied. Octet rule is the valence electrons are summed to be 8. That's the octet rule. You can find the meaning from chemistry courses and other basic semiconductor classes. Yeah, so anyway, also there is ionic bonding, but all these semiconductors are based on covalent bonding for real applications. But quite recently, two-dimensional materials, such as graphene, transition metal, the chalcogenides, graphene, transition metal, the chalcogenides, and so on. These are actually a single atomic layer. In the case of graphene, it's made of carbon. Okay, so carbon atom is aligned in two-dimensional plane. So, but those single layer could be connected into another single layer like this. There is actually bonding, and in this case the interlayer bonding is van der Waals. Okay, it is based on van der Waals force. Their potential potential shapes are all different. Okay, so there could be certain arbitrary potential shape to describe different kinds of bondings. So it might be very complicated. Okay, so there are not so many people who can even induce the shape of interatomic potential. But point here is, even though there might be very complicated bonding potentials, still we can make it simple by an approximation. So here let's say we have potential shape U drawn by this solid line. U is positive, then it implies there is repulsion between atoms. Okay. U is negative, it implies there is an attraction between atoms. Okay. So the nature prefers to be in lowest energy position always. This is the lowest energy position. So even though potential shape is very complicated, near the minimum point of potential, we have Taylor expansion of the original shape as shown here. So there might be very complicated potential shape, and minimum point is at x equal x0. So we expand the potential ux prime near x0, then u x0 and du dx prime. X prime is actually the independent variable here. So x prime minus x0, first order, and then second order part is here. Half d square u dx prime square, then x prime minus x0 square, then higher order component. Okay, but here we consider the x prime near the equilibrium position, minimum potential position. So take the power of 3, then it will be very small, so it will be ignored since they are considered to be smaller than the first order term and second order term. And then du dx prime should be 0, okay, because it is at this minimum point. So first derivative should be 0 at the minimum, so this must be 0. So leading term is actually this one. Okay. So and surely this is non-zero, it is depending on the shape of u. But potential is only important relatively as we increase as we change the position, how the potential varies. The difference is important. So just for convenience sake, sometimes we set this to be 0. Then the equation becomes very simple. We only have this part, okay? And x prime minus x0. The position with respect to the minimum point is now set to be x. And this one, it might be very complicated, we don't know, but we just call it spring constant. Okay, so actually we go through these processes in many new materials. So even though the atomic potential could be very complicated, we just simplify u to be like this, and as a function of x from the change, this is the minimum position, x0, and x0 is the distance between atoms where you have minimal potential. So probably the distance, average distance between atoms will be x0. Then x0 is called as lattice constant. So this is actually very important concept of the applications of any applicable devices and materials. Lattice constant. And this distance x prime minus x0, the change from original distance. So this x, the change from the original distance is actually proportional to strain. I mean, more exactly it is, you need to consider a little bit more additional concepts. But it is roughly has the meaning of strain, okay? Or some mechanical classes, you will see deformation. So this X has such meaning of strain or deformation. And those are actually very important topics recently. And this X can be measured in crystals or semiconductor materials. Also X sometimes can be changed externally by applying pressure or temperature, so we can change X. And K, the spring constant, is actually material parameter. So when you have certain material, then you have fixed value of K. Okay, then we call it material parameter. So each material has determined value of K. And also when you have new material, you might create new crystal structures. Then actually we measure lattice constant, we measure band gap, and as you change the strain, we check out potential shape, and we measure, we identify the material parameter of K in that way. So whether we solve the rather complicated Schrödinger equation based on this harmonic oscillator or not, we somehow understood the importance of harmonic oscillator now, right? Okay, and the final solution of this Schrödinger equation, okay? If we have this potential shape, then you will have certain discrete energy positions with certain quantum numbers. These are the solution actually. Energy eigenvalues for a harmonic oscillator. You need to go through quite complicated Schrödinger equations, but it's rather complicated. Everybody can solve it, within like 1 week. But for this class, I consider to understand the meaning of the solution is more important to calculate the details, okay? If you can calculate the details, still is good, even better. If you understand the meaning, it is okay. So the energy levels here is actually expanded, blowed up, closed up. And N is the quantum number. Here, in the case of harmonic oscillator, we start from 0, okay? The quantum number starts from 0, and these are the actually corresponding energies, okay? So you will see that n plus 1 half, then h mu. Right? So quantum number starts from 0. The separation between any energy level are multiples of ha mu. Okay. So actually you will also see that this is the concept we see from the black body radiation, right? So you can see that when a black body is heated, then there are discrete energy levels separated by h mu, okay, ha mu, the Planck constant multiplied by frequency, okay. So if the carrier is in the excited state, if it goes down to lower energy state, it will emit the light h bar omega or h mu. So that's why the emitted light is related with the discrete energy. Okay. So those are sort of intuitive picture of harmonic oscillator, and you will repeatedly find the related concepts as listed here in many other research papers. Schrödinger equation. Now Schrödinger equation for the harmonic oscillator is minus h bar square over 2m d square psi dx square plus potential energy part 1 half kx square psi is equal to energy E psi. Let's introduce dimensionless variable y because x has the dimension, so we want to change this into a mathematical equation. So this is actually physical equation. We have dimensions here and here. Energy has also the unit. So we set x equal to ay, and then dx should be a dy. We put this into here. Then we have this equation. This one minus h bar square over 2ma square. So we want to remove this, so we divide both sides of the equation by minus h bar square over 2ma square. And then you will have this one. So it is actually a simple procedure, everybody can do it. So minus m square omega square a to the power of 4 h bar square y square psi equal to minus 2ma square over h bar square e psi. Here let's set a at square root to h bar over m omega. Then you will see this is actually 1, and you will see epsilon. Let's set this one, epsilon ma square e over h bar square, applying the definition of a here. Then we have this one instead of a, then h bar subtract with each other, m subtract with each other, then energy divided by h bar omega. Their unit is just the same, right? So their unit is just the same. Then we will see that it is dimensionless. Or unitless. Okay, we only have numbers. Okay, so now we have mathematical equation here. Okay. Right hand side move to here, then it becomes like this. You will see that the potential energy has inversion symmetry, right? So U minus X equal to U plus X. Then wave function should have parity. So wave function should have either even parity or odd parity. And also the lowest energy state will be with even parity. We can consider the dimension of A is actually equal to length. So please check it out yourself. In my case, I will consider the unit in CGS unit. CGS unit. Then H bar, I remember 6.1 multiplied by 10 to the minus 16. The unit is electron volt sec. Okay. Then mass M unit is in CGS unit is as electron volt. Omega sec inverse. So you will see that this one subtract with each other. Unit is second. But here second actually has the same unit with length because CGS unit is the unit where we set velocity of light. Velocity of light. 3 by 10 to the 8 meter per sec is said to be 1. This is the CGS unit, and it is actually useful in the case of materials and devices. Now you will see many cases we use CGS unit when we deal with semiconductors, especially because we can easily figure out the concept based on electron volt. Okay? So actually this temporal scale is actually length scale in CGS unit. Anyway, so this is basic idea to solve Schrödinger equation. We want to make it pure mathematical equation, and solution of this mathematical equation is well known from differential equation classes. We just copy from there. So Schrödinger equation is now simplified like this. To find the solution to this differential equation, we first analyze its asymptotic behavior. Actually, this is very typical approach. Okay, when the equation is too complicated, we always want to make it simple, and usually we consider asymptotic behavior. Okay, so actually this is taken from the differential equation class. Firstly, we look at small energy, then y squared term dominates. In this case, small energy, it means epsilon is very small. Epsilon was proportional to energy. Okay, so let's say it is very small. Then y psi double prime equals to y squared psi, which suggests that the wave function may include a Gaussian, because second derivative induces y squared term. Okay, so each derivative will induce linear term. So That's the case of Gaussian. This is Gaussian. Okay. Exponential. Minus y squared over 2. Okay. So if we take the derivative, you will see minus y is multiplied, right? But surely general function should include some additional function we don't know. Thus we presume that psi has this formulation. Then we take the first derivative u prime, then psi prime, then u prime e to the minus y squared over 2, then minus u, then we take the derivative on the Gaussian part, y e minus y squared over 2. We take the second derivative here, then u double prime e minus y squared over 2 minus u prime, we take the derivative of this, then y e to the minus y squared over 2. I think because we take the derivative from here, there comes minus y. Okay, yes, so it is minus here. And then this one, partial derivative. So we take u prime first, u prime y to the minus y squared over 2. Then minus u, we take derivative on y, then y disappears. So u e to the minus y squared over 2. Then we take the derivative from this, then minus y goes down, so minus y and minus y multiply them. Then we have y squared, so u y squared by e to the power of minus y squared over 2. And they all share e to the power of minus y squared over 2. So we arrange the other terms as shown here. Okay, so we put this into here. Okay. So this is the equation now we have, right? Oh, not here, I'm sorry. We should put it here. Okay, not here. This is just the simplified case, but general case with energy epsilon. Energy time epsilon. Then we expand this. Then both sides divide by this one. We ignore this part now, right? Then it is simplified like this. Okay. So now second order differential equation. Okay. With respect to u, right? And still is quite complicated equation, okay? And actually mathematicians provide how we solve this equation, okay? Based on power series, okay? Because u is not hardly, it's hardly available in terms of analytic calculation, so we rather apply the idea of power series. So u is said to be linear summation of Cn Yn, okay, power series. So n is changing from 0, so we put this 0 and then we have C0, put the n with 1, then C1 y, and n is 2, C2y squared. Linear summation continues. and then we take the first derivative and the second derivative. First derivative becomes cn y to the power of n minus 1. Okay, if we put n into here, this goes 0, so n equals 0 term doesn't survive. So, and then if we summarize, if we sum this linear power series from starting from 0, then we change this subscript into n plus 1, right? So easy to follow, right? So also u double prime, is given here. Okay, it can be starting from n equal 1. If we want, you can change the formation to start from n equals 0, right? Also, because in this formation n equals 0, this goes 0, n equals 1, this goes 0, so actually they are just the same, set to be the same. Okay. So I think actually even though you cannot calculate the mathematical details for the Schrödinger equation, still it is okay as long as you understand the intuitive picture of a harmonic oscillator and basic idea to change the physical variables into mathematical variables, okay, which were dimensionless. The procedures are actually taken from differential equation classes. It's now purely mathematical. So I didn't develop at all about these processes. I just learned from mathematicians. So anyway, now substituting those power series into equation, we now have this. Okay. And analyzing the resulting series solution, we arrive at recursion relation between Cn and Cn plus 2. Okay. So actually you just summarize. You can make it simple, in terms of y to the power of n. Okay, then this one will be changed like c. This one like Cn plus 2, and then n plus 2, and then this one n plus 1. This one, okay. If we just make it simple in terms of y to the power of n, then it will be changed, and you summarize the others, okay. Multiply by Cn. Then if this to be 0, then there should be a relation between Cn and Cn plus 2. So if lower n value, like something like C2 for example, we don't know C2 yet, but at least if we know C2, then C4 is determined, right? And then we multiply it by like 4, 3, we put it 2 here, then 5 minus 2 epsilon, something like this. Okay, so this is the power series added all the way into infinity, so it n goes very large, so in the limit of large n is very large, so we compare n with 2, then 2 is ignorable, 1 is ignorable, and these are just finite values, so they are ignorable. Then we have this relation, okay? Because there's n and n square we have. That's the way we have this one. So, in terms of C0, based on this recursion relation, we can calculate Cn, okay? And now U was defined like this, and Cn is like this, okay? In the case of even number, even integer n, so we separate that into even and odd value. Odd term we don't know yet, but at least even term we figured out the relationship between n and n plus 2. We apply that idea into this part. Okay, so if n is even, then n is replaced by m, so n is even, so let's say n is 2m, okay, right? So here n was even, so we don't have any restriction about m anymore, so m starts from any number, even or odd. So we put this into here, then it's simplified like this way. This one goes to m factorial. So actually there might be negative value of m or 0 value, then we always set to be 1. If it is negative, still we set it to be 1, okay? To make it simple for now. But important thing is this mathematical form goes to infinity, okay? So, and it is approximately known to be C0 is just a constant. This one, yeah, y to the power of 2m multiplied by 1 over m factorial is known to be the Gaussian function e y square, and there are more. Easily we can see that because wave function psi is known to be u multiplied by Gaussian function as shown here. But if it is e to the power of y square, we multiply them, then this goes to actually infinity as y goes infinity, and y goes infinity when x goes infinity. And from previous potential shape of u, okay, if x goes infinity, the potential is approximately goes to very large. So potential is approximately going very large. So wave function should goes to 0, okay, instead of infinity. So something is wrong here, right? So in this case, we see that the numerator of e this one should be 0 at some point. Okay, if it's non-zero and if it survives, this recursion relation survives, then it is added into infinitely large terms. So this correlation works always unless numerator is not 0, and this relation is actually physically wrong. If it's true, it always diverge. I mean, wave function psi will diverge, which is not right. Okay, that's why the numerator of this equation should be 0. That's the most important finding in this slide. Okay, so if you can understand the meaning, still it is okay, good enough. The numerator should be 0 at some point. So n is changing from 0, 1, 2, 3, 1. Okay. Like this. So at some point epsilon should be the same. Yeah. To this one. With this one. So numerator should be 0. So we have 2 epsilon is now equal to 2n plus 1, and now epsilon is equal to n plus 1/2. Okay, that's why, yeah, the definition of epsilon was this one. That's why we have this energy relation. So that in order to have any physical solution not diverging, okay, we always satisfy this discrete energy values, h bar omega multiplied by n plus 1/2. And here important thing is n starts from 0, okay, not 1. It starts from 0. Okay, thus energy levels for the harmonic oscillator are quantized. And this is the form of quantization. So this is the energy, and we put this into here. So this is the mathematical form, and could be 0, 1, 2, and so on. Okay, and for each integer value, the solution is known to be Harmonic polynomials. Okay, if we put that Harmonic polynomial, we can calculate the wave function psi like this. It looks a little bit complicated, but actually the Harmonic polynomials are known to be like this. And we always care like a lowest energy state. At best, 3 lowest energy state in most of semiconductor materials and devices. Yeah, many cases we use the lowest energy state. Sometimes we use second lowest or third lowest, and we consider carrier excitation and relaxation between different energy levels. So, 0, 1, 2, this is enough. Okay, so in the case, the Harmonic polynomials are not that complicated. Okay. And then wave function shape is here. So 0, 1, 2, those are applied here. Okay. And quantum number n starts from 0. Yes, instead of 1, it starts from 0. wave functions for higher n have more humps, like this. So if we draw this wave function shape, we have this for n equal 0 state, n equal 1 state, n equal 2 state. Please note that psi 0 is even parity function, psi 1 odd parity function, psi 2 even parity function. Okay. If we take square of wave function, that's the probability to find the particle at certain position. Then we have this structure going up and going down, psi 1, going up, going down, going up, going down, psi 2 dashed line, changing more rapidly. This means psi 2 has the smallest wavelength among them. Okay. So actually, if you read through Kang Chen's textbook, you will understand the detailed procedures. Okay. The meaning of solution is written here, and this is actually taken from Kang Chen's textbook. Some of the terms you will find in research papers. Let me just read through. Harmonic oscillator model is important for understanding the absorption characteristics of gases in the infrared spectrum. When a photon interacts with the gas, absorption occurs only when the photon energy equals the energy difference between the final state and the initial state of the molecule. So there are several energy levels. Let's say energy was originally at initial state and it absorbed the light. It goes to higher energy state. Their energy separation is the instant photon energy. For the vibration modes of molecule, equation leads to the frequency is mu multiplied by delta n. I mean, it is absorption, but there could be also emission. Original state could be higher, it goes down to emit the light, right? So depending on whether it is absorption or emission, delta n could be plus minus 1. Okay. This is something called selection rule. The absorption or emission of a photon occurs when the photon frequency equals the molecular vibration frequency. Vibration frequency, this is actually something called phonon frequency. But here we rather use vibration because it is gas or molecules. So there are not so many atoms, but phonon is actually the terminology describing atomic vibrations in crystals. It is actually very important topic. In crystals, there are not only one atom, but extremely many atoms. They are connected with certain spring constant K. They move around, and then the low part also discuss the molecules. Okay, so if we were involved in the studies of some chemistry like molecules, gases, then this might be very useful. This is the case of CO2 molecules, and different vibration modes will have different energy state. Okay, and different energy state has different energy values. So a certain energy level can be defined like this, and the other energy level can be defined like this. You have like EI for this one, and EF could be this one. So depending on the light absorption, if they are resonant, if this energy separation is the same with h bar omega instead light energy, then we call it resonant. Then this mode becomes different mode of this. So these are different kinds of molecular vibrational modes. Okay, and we can describe this kind of vibrations in crystals, which might be more important in applications. So you can read through yourself. This is the basic idea. Once you understand this, still is okay if you don't understand the details. Still is okay. And then we apply some of the ideas to describe things related with phonons, the atomic vibrations in crystals, in advanced classes. Okay, that's it for today.